students. So in today's session we are going to learn some more properties of D and F block elements. In that the first one is magnetic properties of transition elements. So magnetic properties are basically three types, means they are paramagnetism, paramagnetic, diamagnetic or ferromagnetic. So in this session we are going to learn only for this lesson we are going to see only paramagnetic and diamagnetic. So paramagnetism, all transition elements we already know they contain unpaired electron, that is why it comes under a D block element, that means a transition elements, right. So paramagnetism, that means the elements who are having unpaired electrons, so when they are having unpaired electron they can easily attracted by the magnetic field. So the elements with the unpaired electrons which are attracted by the magnetic field, that substances are called paramagnetism, that means they show paramagnetic nature. Yes, and next one is diamagnetism. Diamagnetism means the substance which do not contain unpaired electrons or they are having fully filled electronic configuration and they are repelled by the magnetic field. Understand children? Diamagnetism is nothing but the elements who are not having unpaired electrons or they are having fully filled electronic configuration, so then they can be repelled by the magnetic field. When they are not having any unpaired electron or they are having fully filled electron, then they will be automatically repelled by the magnetic field. Then such substance comes under diamagnetic substances. That property is called diamagnetism. And ferromagnetism is a special case of paramagnetism, that is ferromagnetic substances are strongly attracted by the applied field and magnetized permanently. Understand children? They are magnetized permanently. So here, so what are the elements who are having unpaired electrons? So how they are show magnetic field means, to calculate that we are having this one called magnetic moment. Okay, magnetic moment which is represented in a Greek letter that is called as mu. Okay, which is expressed in the form of mu, and its unit is Bohr magneton, BM. Okay, Bohr magneton. So in this case we are calculating only spin only magnetic momentum. So the magnetic momentum of any substance arises from spin and orbital motion of unpaired electrons, but here we are learning only spin only magnetic momentum. Magnetic momentum or spin only magnetum are both are same, both will be having same formula, that is mu equal to root over n into n plus 2 Bm, where n is the number of unpaired electrons. So the elements who are having unpaired electron only they can show paramagnetism, right. So here by this formula, with the help of this formula mu equal to root over n into n plus 2, we can find how many number of unpaired electrons are present in an element. So where n is the number of unpaired electrons. So here I have taken one example. Calculate the magnetic moment of Mn2 plus. So Mn2 plus. So here in transition elements you have to know their electronic configuration children. So Mn2 plus, that means it's already donated 2 electrons. So their electronic configuration, last electronic configuration is 3d5 4s0. Yes, 3d5 4s0. It's already have donated. So it is having 5 unpaired electrons where n equal to 5 here now. So here n equal to 5. So substitute in the formula mu equal to n into n plus 2, where root over 5 into 5 plus 2, that is 5 into 7, that is 35. Okay, root over root 35 Bohr magneton. As it is having 5 unpaired electron, it is having magnetic moment is root 35 Bohr magneton. So in case of nickel plus 2, look at here children, the electronic configuration is 3d8 4s0. So 3d8 4s0 means you have to arrange the electrons in this way, 1 2 3 4 5 6 7 8. So here how many unpaired electrons are there? 2. So never write how many unpaired electrons means 8, because 8 means you have to substitute in their suborbitals like this. Yes, 3 will be paired and only 2 will be remaining as an unpaired electron. So here n will be 2. So magnetic moment mu equal to root over n into n plus 2, that is root over 2 into 2 plus 2. So 2 plus 2 means 4, 4 into 2 is 8. So root 8 Bohr magneton. So this is how you have to calculate the spin only magnetic moment or magnetic moment of an element. So what did you understand by this magnetic properties of transition elements? The magnetic properties are of three types: paramagnetism, diamagnetism, ferromagnetism. So magnetic property mainly depends on the number of unpaired electrons. So paramagnetism means they are having unpaired electrons, diamagnetic means they are not having unpaired electrons, and they are having fully filled electronic configuration. And ferromagnetism is a special case of paramagnetism. That means the substance can be attracted strongly by applied field and it can be magnetized permanently. So to calculate number of unpaired electrons, so the formula is mu equal to root over n into n plus 2. So here we are taking only spin only magnetic momentum, because in many compounds of 3D series elements, the angular momentum due to orbital motion of unpaired electrons is small, and it can be, because of it is small, it can be ignored. Therefore only spin only magnetic momentum only we are considering. Understand, children? So this is the magnetic property of transition elements. Next comes to color property. So we already discussed in the early of this chapter, this elements exhibits DD transition, isn't it? So when an electron moves to the higher level and again when it moves to the lower level, it exhibits some color. So that only we are going to see now. Generally all transition elements are colored except scandium 3+, titanium 4+, zinc +2 and etc. in the first 3D series. So this elements comes under first 3D series. So why they are exhibiting color? Because they exhibit color due to the presence of unpaired electron. As they are having unpaired electron, they can exhibit color. So how they can exhibit color? Because the unpaired electron which undergoes a DD transition, they undergoes DD transition. So how we are saying, this is the lower level, this is the higher level, children. This is an unpaired electron. Okay, then the electron which is present in the lower d orbital, when some radiation, when it absorbs certain amount of energy from visible spectrum, what happens? They get excited. But the electron which in the higher energy level is unstable. The electron which is present, which means excited to the higher level, will be unstable. So when they return to the ground level, as it is unstable, it return back to the ground level. When they are moving to the ground level, they will emit certain radiation. Due to this radiation, they exhibit some certain color. Okay, they exhibit certain color with some radiations. Understand, children? So look at here, when the unpaired electron which is present in the lower level gets some radiation, certain amount of energy from visible spectrum. So when they get energy, they will excite it to the higher level. In the excited state, the electron will get unstable, means it will be unstable. As it is unstable, again it moves down to the ground level. When it is moving down to the ground level, they exhibit a certain color. Okay, with some radiations, they exhibit some color. Understand? So this is how the color property of a transition elements are present. So here I have taken one example, titanium 4+. So here I said titanium 4+ will not exhibit any color. So what is its electronic configuration, children? Organ 3d2 4s2. Yes, 3d2 4s2. So here we are saying 4+. So all the 4 electrons were removed from the titanium. So that means no unpaired electron is present. When there is no unpaired electron is present, the titanium is colorless. And next comes to Zn+2. Zn+2 electronic configuration is organ 3d10 4s2. So +2 means you have to remove these 2 electrons, and inner d orbital is completely filled. Okay, that means here unpaired electrons are 0. Sometimes the question may be asked, why the zinc exhibit white color? Why white means nothing, isn't it? Why? Because they are not having any unpaired electrons. So that is why it is colorless. So this is about colored property of transition elements. Next comes to complex formation. So next property is complex formation. The transition metals form a large number of complex compounds due to the comparatively small size of the metal ion. Okay, and they are having metal ion, and due to their high ionic charges and the ability of d orbitals for the bond formation. So what are the main 3 characters you have to remember under complex formation of transition metals are due to its small size. As it is having small size, they are having high charge density. They are having high charge density and the availability of vacant d orbitals. They are having vacant d orbitals. So when they are having vacant d orbital, the respective ligands can occupy that place. They can form a compound. So the elements who wants to donate an electron, they can donate easily. They can placed under this d orbitals and they can form complex compounds. So here some example: iron Cn6 okay minus 4. This is one compound, and here another compound Cu and H34 plus 2 whole to the power plus 2. So these are the examples of complex formation. Complex formation, why it forms a complex formation? All the transition metals form a large number of complex compound due to its small size, high charge density and availability of vacant d orbital. And comes to the next property, catalytic property. So catalytic property, we know all the transition elements can act as a good catalyst. All transition elements can act as good catalyst. So what do you mean by catalyst first? Catalyst is nothing but a substance which increase the rate of chemical reaction without undergoing itself in any chemical change. So catalyst is a substance which increase the rate of chemical reaction without undergoing any chemical change. That means this catalyst will not undergo any chemical change. So some of the examples are vanadium pentoxide, V2O5, in the process of contact